Okay, so we are continuing in chapter 3. I'm going to wrap up the stuff from the section we had been working on by talking about combustion analysis today. And then Monday, we're going to look at the last couple of sections on molar concentrations. So over the weekend, I'd like you to look at sections 3 and 4 in chapter 3. Start off by just seeing what the objectives are, seeing what the topics are. Have you seen this before? Does it look familiar? And then I've got a prepare to learn for you to do about those two sections. And then after we talk about it in class, make sure you go back and read that section a little more thoroughly. Make sure that what you have in class and what you read in the book are making sense together so that you can ask questions if you need to. Looking ahead, we'll be then getting into chapter 4. So the vocabulary for chapter 4 will be due that Friday. Also that Friday, we will do a quiz. Now the quiz will not cover any, the quiz on Friday will not cover anything in chapter 4. So it's going to be mostly over chapter 3. I didn't put balancing on the test, so balancing equations will be in there, but also everything that's bold on your polyatomic ion sheet, the acids, the molecules like water and ammonia that we should know, all of those are fair game for your quiz. So on your test, I had 2 or 3. I'll probably have more on the quiz so I can make sure you know all of them and not just spot check. Yes.
Wait, so is the quiz the Canvas one that you put in, or is it
No.
the paper one?
It will be on paper.
Okay.
Yeah. It may be listed on Canvas, but it will be on paper.
Yeah.
Okay, questions? All right. Next week, I will also have to move my office hours again, this time due to a doctor's appointment. Since we have the quiz on Friday, if you have any questions and you need them answered on Thursday, please email me. I will try and find a time around my doctor's appointment that I can fit you in. I should be back on campus by 3:30 at the latest. So later in the afternoon is a time when I can probably meet with you. Okay. There are no other questions. We will be moving forward. Let's see. So we had talked on Monday about empirical formulas where when we divide by moles, we don't get nice whole numbers. We might end up with like 1.5. And so then we have to make a little bit of an adjustment by multiplying by a number, right? So we'll see some more examples of that, see what to do with that again today. We also talked about going from the empirical formula to the molecular formula if you knew the molar weight. So there was one question like that on your test. And today we're going to talk about combustion analysis. So this is basically how do we come up with those numbers of what the empirical formula is from experimental data, not just being told the percent mass. So we're going to look at that. Now, when we do combustion analysis, it is almost always organic compounds. So when you hear the word organic in chemistry, you should be thinking carbon. The combustion means we're burning it. So organic is going to be carbon and hydrogen mostly. There are some examples that don't have hydrogen. We're going to ignore those. And then it may have oxygen, nitrogen, sulfur, sometimes phosphorus. When you have these, they create what are called functional groups. So depending on how the oxygen is attached or how the nitrogen is attached, it will be a different functional group like an amine or an alcohol or carboxylic acid. And so as you go through chemistry, you'll hear more of these terms and begin to recognize them. But right now, we're going to focus on when we only have these two elements. So if there's only carbon and hydrogen, we call this a hydrocarbon. Okay, so if we are going to burn a hydrocarbon, so here I have X and Y because we don't know how many carbons and how many hydrogens there are. If I burn this, I need something else. What do I need? Oxygen. Pretty much no matter what the hydrocarbon is, whether it's propane, methane, ethane, all of those, butane, octane, all of those are going to produce the same products. And in fact, if I add oxygen on here, so I make it methanol, propanol, ethanol, alcohols burn as well, I always get the same products. So this makes it really convenient to figure out how to go from the products back to the original, because we always know what products we're going to get. Now, this is the kind of critical thinking that's really important in your chemistry classes. In history and in English, you might be talking about writing a paper and supporting your points with evidence and things like that. In chemistry, sometimes when we talk about critical thinking, we're talking about making connections between what we know and what we want to know, and seeing how we can get from one to the other. So this is kind of the beginning of stoichiometry. So I know that's that big scary word that's coming up in chapter 4. Please don't panic. I'm going to guide you through it. But what we're going to do is we're going to use our understanding of conservation of matter or conservation of mass, which says that we can't create atoms and we can't destroy atoms. So when I see this carbon here, all of the carbon in my product had to come from reactant, right? So if I know how much carbon is here, I can figure out how much carbon was here. Similarly, all of the hydrogen in my water had to come from my reactant, right? There's no other hydrogen on this side. So if I know how much water I have, I can figure out how much hydrogen I have, okay? So I'm going to go from the mass of the carbon dioxide to moles of carbon dioxide. And because there's only one carbon in each carbon dioxide, that's going to be equal to the moles of carbon. So all I have to do is figure out how many moles of carbon dioxide were produced, and I know how many moles of carbon I had. With the water, I get to moles of water, but there are 2 hydrogen atoms in each molecule, right? So for every 1 mole of water, I actually have 2 moles of hydrogen, okay? So when I figure out this number of moles, it's actually only half the amount of hydrogen because I have to count it twice, okay? Now we're going to walk through the steps of doing that, but I kind of want to give you a picture of what might be happening. So first of all, in chemistry, we use symbols, sometimes with the arrow, to indicate what's going on. So a triangle means heat. So if I wanted to say I was burning this, I might put a triangle there to say I was burning it. And I'm going to have some sort of oven that's going to have my sample in it. So this blob is my sample. And my sample is this hydrocarbon, CXHY. So I've made something in the lab. I think I know what it is. And I'm going to go and try and determine if my ratios make sense for that. I'm going to have to pump in some oxygen. So I'm going to have O2 that's somehow going to go in this chamber. And then I'm going to blow that oxygen so that everything goes out through one tube. This is going to go into another chamber. Now this next chamber is going to have some sort of solid that will absorb, and it's going to be one of 2 things. It can go in either order. Let's say it absorbs the water, okay? If you had lab, did you use the little glass container to put your crucible in?
The desiccator, yeah.
Yes. So desiccate, sec refers to dry. Desiccate means to draw the water out. So let's say we had those little rocks down here,
Yeah.
okay? They absorb the water. We could weigh the rocks ahead of time, then do this analysis, and then weigh the rocks afterwards. And if they absorbed water, the difference in the mass would be how much water was absorbed, right? Okay, so this chamber, we absorb the water. Okay, but we keep that air going to the next chamber. And we do something similar with carbon dioxide. So there are a few things that can pick up carbon dioxide. And so we would have some kind of rock or sample over here. We'd weigh it ahead of time. And then as we have all of that air moving through, the carbon dioxide would become attached to it, and we would determine how much carbon dioxide there was. When we're doing this professionally, there's a chance we might have these other ions, and so you could go on and have additional chambers to check for other things. We're going to keep it simple and keep it to this. Okay, so from these two chambers, we can determine what's the mass of the water, what's the mass of the carbon dioxide. Once we have mass, we can go to moles, and moles is the key to everything. Okay, so we are going to do an example here. We're going to follow this. We're going to convert our carbon dioxide and water to moles. And in order to go from mass to moles, what are we going to need to have? Of course, we need the mass, but what else do we need?
Grams per mole.
Grams per mole, which we sometimes call formula mass, molar weight. Okay, so we will use that to get moles. Once we have moles of carbon dioxide, we already have moles of carbon. Once we have moles of water, we're going to have to multiply that by 2, and that's going to give us moles of hydrogen. And then once we're at the point that we have moles of elements, we're right back where we've been from every other empirical formula problem. We have to divide by the smallest number of moles, and that's going to tell us the mole ratios. Okay? So in our example, we are going to use naphthalene. It's used to make mothballs, and it is a hydrocarbon. So that tells me the only thing I have to worry about is hydrogen and carbon. I don't have to worry about anything else. So in the combustion analysis of this compound, where we don't know what X and Y are, we produce 69 grams of carbon dioxide and 11.30 grams of water. Okay, so if you like, you can use the equation to keep track of things. So this is our mass. We need the formula mass. Do we remember the formula mass for water? 18.02. All right, you may not have carbon dioxide memorized, but oxygen is 16, right? 2 16s is 32. How much is carbon? 12. So we need 32 plus 12. Jot it down on your paper. There's no carrying. 32 plus 12. You think? You knew it? 44. Okay. But of course, carbon is a little bit more. So we're going to say 44.01, right? The carbon was actually 12.01. Okay. All right. Now, since I have more than 44 grams, I should have more than 1 mole. I have less than 18 grams, so I should have less than 1 mole of water, but then I'm going to multiply it by 2. So I might end up with more than 1 mole of hydrogen. Okay, so let's do our unit analysis. It is very, very important, oops, this is the carbon dioxide, that we keep track of what chemical we're doing. One of the most common mistakes I see people do on a test is they'll put in a number and then they'll forget what chemical they're working with. And then suddenly they're multiplying by the formula mass of something else. or they forget that they're still at water and haven't converted to hydrogen. So we're going to try and keep the chemical with it so that we know the whole way which chemical we're talking about. Okay, so for the unit analysis, we multiply by that conversion factor, that fraction that has these units on the bottom. These are the ones we want to get rid of. Grams of carbon dioxide, and we want to go to moles of carbon dioxide. So for other things, I might just leave it as grams and moles, but when I'm converting from one chemical to another, I'm going to keep that label of what chemical it is. So 1 mole of carbon dioxide, we said, weighs 44.01 grams. And then I'm going to go ahead and add the last conversion factor on here so we can see how they cancel out when they line up. So I don't really want moles of carbon dioxide. I want moles of carbon. Okay, so I'm going to put 1 mole of CO2 on the bottom and 1 mole of carbon on top. All right, so multiplying by 1, dividing by 1, is that going to change my number? No. No. So if I happen to forget for carbon, it's not going to make a difference. But if I forget for hydrogen, it will throw my numbers off. Okay. So I'm going to take 69 times 1 times 1 divided by 44 divided by 1. All right. Now I recommend that you pull out your calculator, try and do these calculations. I'm going to do a second example where I'm going to ask you to do it on your own. So if you have your calculator, you might pull it out. I'm going to go ahead and tell you the number I got here. You check and see if you get the same number. Okay, so round it to 4 decimal places because I have 4 and 4, or not decimal places, 4 sig figs. Since I have 4 and 4, I'm going to report 4 in my answer. Now for my units, I'm going to look at what's left over. So I have grams of CO2 and grams of CO2. I can cross that off. I have moles of CO2 and moles of CO2, one on top, one on bottom. I can cross that off. So I'm left with moles of carbon, which is what I want.
Why is 1 mole of carbon equal to 1 mole of CO2?
Because every molecule of CO2 has 1 atom of carbon. So if I were making a car and I had 100 steering wheels, how many cars could I make? 100. Okay. So if I ended up with 100 cars and I wanted to know, well, how many steering wheels did I start with? I would say, well, there's 1 steering wheel. Okay. All right, so we're going to do similar treatment for the water. Keeping track that the 11.30 grams is for our water. Our conversion factor is going to have grams of water on the bottom because I want to cancel grams. And it's going to have moles of water on top. Okay. When you're trying to figure out where your number goes, so the 18.02, do you put it with the grams? Do you put it with the moles? You're going to have it go with the first unit in the molar mass. So since I write 18.02 as grams per mole, it's the 18.02 is going to follow around the grams. Wherever I put the grams, that's where the 18.02 goes. All right. Now I want to get to hydrogen. So I have 1 mole of hydrogen. I'm just doing a ratio here. I'm obviously going to have a different number of moles of the water, but I'm saying the ratio of water to hydrogen is 1 to 2. So I put 2 moles of hydrogen. The moles of hydrogen is what I want. So I want that on top. The moles of water is what I want to get rid of. I want to cancel it, and that's why I put it on the bottom. Okay. So I plug all of that in, and I get 1.254. Anybody else get that? Lanad's good. My grams of water cancels, my moles of water cancels, and I'm left with moles of hydrogen. So this is moles of hydrogen. Okay. So now we are back in familiar territory. We have moles of elements, just like we did when we did the percent composition. We got to the moles of the elements. We need to divide by the smallest number of moles. So which am I going to divide by, the carbon or the hydrogen?
Hydrogen.
Hydrogen, because there's less of it. And at this point, we say the moles cancel out. So we don't really have units anymore. We just have the ratio for the elements. So the ratio of hydrogen to hydrogen is 1. Now, is that going to be, it's obviously more than 1 because this is a bigger number. Is it going to be as much as 2? No, because in order to be as much as 2, it'd have to be 1.2 to like 2.4 or 2.5. So when I do this math, I end up with 1.25. Okay. So when I don't get nice, pretty numbers, now these are sort of pretty. They're not like, random numbers, but they're not whole numbers. Then I look at the decimal part, the 2.5 here, and I ask myself, what fraction does that remind me of?
1/4.
1/4. Okay, so
times
1 over
by
4.
4.
So you multiply it by 4 because that's the bottom part of the fraction. So I'm going to do 1.25 times 4 and 1 times 4. Okay, so this is going to give me 5 carbons and 4 hydrogens.
That should be the empirical formula.
So put them together, I should get the empirical formula C5H. Okay, so this would be the answer. Now, if you were to do a search for the molecular formula of naphthalene, which is the compound we said we started with, we would find that the molecular formula of this is actually C10H8. Did we do something wrong? No. Remember, the molecular formula tells us how many atoms are actually in the molecule.
Empirical is the smallest ratio.
Empirical is the smallest ratio.
Well, smallest whole number ratio.
Smallest whole number ratio. So here I have the numbers that are both even. So this ratio is the same as this ratio.
Yeah.
Okay. So that checks. Did that correct?
Yeah.
All right. Okay. So I'm going to put up the next one. Feel free to work with the people near you. Try and sort out. If you need help, you can ask me. Yes, please use your calculator.
Oh, use it, okay.
Yes, please use it.
Okay.
Unless you do math like my husband does, where I just shout numbers at him and he's like, oh yeah, this is the answer.
I can't do that.
He's a math teacher, so Okay, so this is example number 2, and I'm going to write on the board what question you might see. Rather than just giving you the data, I'm going to say, So you might read a problem that says combustion analysis of a hydrocarbon gives 81.9 grams of carbon dioxide and 39.1 grams of water. Find the empirical formula. So whenever you see the direction, find the empirical formula, that tells you you need moles of elements. Okay, so even if you don't know what else to do, there's a clue in there that tells you, okay, I gotta somehow get to moles and they need to be moles of elements. Okay, so I'm gonna put the setup on here, but you work, you know, you can do it by yourself if you want to, you can work with people around you if you want to, see what you can get. So the actual chemical naphthalene happens that we can't tell that from the information given to us. But since we know the name, we could look it up.
Both the CO2 and water?
No, you're trying to find the empirical formula of this.
Okay, of the hydrocarbon. Okay. That can get a bit funky without specification.
If you get stuck, use the first example to try and figure it out. This was the mass, that's what's changed, but everything that we multiply by should be the same going forward. Okay, so for the moles of carbon, anybody think they have an answer?
1.86.
1.86 moles. Now I notice you only have 3 digits here, whereas over here we kept 4 digits. But we only have 3 digits in our mass, 1, 2, 3. So that's why we're only reporting 3 here. So this is moles of carbon. It also happens to be carbon dioxide, but what we care about is the carbon. Now I know some of you, it's hard to see down this low with my computer in the way, so I wrote the same thing up here. So 39.1 grams of water times 1 mole of water over 18.0102, 2 grams of water, and then our ratio of 2 moles of hydrogen to 1 mole of water, okay? So does anybody have a number for the moles of water? Or, sorry, hydrogen, what? 4.34. Okay. So what are we going to divide by? The moles of carbon or the moles of hydrogen? This time we'll divide by the moles of carbon. So for carbon, we get 1. For hydrogen, I get 2.33. Okay, so not a whole number, but I look at the 0.33 and what fraction does that remind me of?
2 1/3.
Okay, so 2 1/3, or this part just reminds me of the 1/3. So I'm multiplying by 3 because 1/3 has 3 on the bottom. Remember to do to the carbon what you do to the hydrogen. Okay, so times 3 for both of these. So my empirical formula is C3, 1 times 3, H, and then 2.33 times 3 is 7.
Okay, because on the calculator it says 6.99.
Okay, and so if you get something that's not a whole number, if you get 6.99, you're gonna look at that next digit. And if the next digit is either a 9 or a 0, then that's close enough to round.
Okay,
All right, next I wanna look at balance. Well, anybody have questions about this? Okay, I will try and do another example on Monday. I wanna look at balancing, since that's gonna be on your quiz. So I have on the board 3 equations to balance. Those 3 are pretty similar in difficulty to what you will see on your quiz. So if you look at those and you've got it, it's super easy, you're fine. If you're looking at it and it's still challenging, then you maybe want some more practice. If you finish those really quickly, the ones on the back are more challenging. So if you look at those, you can see if you really have it down by trying to get those. Those would be worth bonus points. All right, so let's take a look at this first one. Now, before we balance it, does anybody happen to recognize that equation from a biology class, perhaps? Okay, so the C6H12O6 you said was glucose. Cellular respiration, almost, it's the opposite. So, yeah, so this one's photosynthesis. If I reversed it, it'd be cellular respiration. So the plant takes in these things and gives us fructose and oxygen or glucose and oxygen. Okay, so as I'm balancing this, what would I put in front of the carbon dioxide? 6, because I have 6 carbons over there. What do I put in front of the water? Also a 6, because I have 12 hydrogens. And then what do I put in front of the oxygen? This is a little tricky. This one's also a 6. So I had someone in the last class say 9. You have to account for these here. So there are 6 and 12 is 18 on this side. 6 of those are accounted for here. So we need to account for 6 or 12 on that one. Okay. The next one is almost the reaction that you would do for making like a homemade volcano where you take baking soda and vinegar and mix them together. So this is very similar to baking soda. It's not exactly the same compound. And then vinegar is an acid. Now this is also an acid. It's not the same acid. What is the name of this acid? There's no oxygen, so we start with hydro. Hydro what? It's hydrochloric acid. So by far the most commonly used, I got like a hair on my face here. I can't see this. Okay, hydrochloric acid. All right, I'm gonna have to do this blind. Because that's dry, there we go. All right, so do I put anything in front of the sodium carbonate? No. But in order to balance the sodiums, I'm gonna need what? A 2. So that gives me 2 chlorines. So what am I gonna do here? Also a 2. And then what do I put in front of my water? Nothing, because since there's two
Oh, right.
hydrogens here, that balances the two here. Okay, so invisible 1, and then what about the carbon dioxide? So how many carbons over here? 1. How many carbons over here? Also 1. So that's also the invisible 1. And then if you double check your oxygens, they balance as well. Okay. This one down here, is this an ionic compound or is that a covalent compound? So iron is a metal. So what does that tell us? It's ionic. Ionic has metal and non-metal, okay? So if I am to name this, I get to maybe use Roman numerals, but I'm not going to use prefixes, okay? So I would have iron, and then what's the name of this? Sulfate. Okay, so when it's just the ion, it's sulfate. When it's the acid, it becomes sulfuric. Okay, so it's iron sulfate, but do I need a Roman numeral? Yes. And that Roman numeral tells me the charge. So it's not this number. This tells me how many irons. This number tells me the charge. Okay, because when I have the 3 of one and the 2 of the other, all the charge factors. So this is iron 3 sulfate. And then over here, it's iron 3, what's this ion? Hydroxide. Okay. All right. So do you want me to walk you through it, or you want to just give me what you have? Nod your head if you want me to walk you through it. Okay, a couple of nods. All right, so I've got a 2 here. So I'm going to put a 2 over here with this iron. Okay. Now, I have the same ion here, sulfate, as I do here. And I have the same ion here as I have here. So I'm going to treat that as just one thing. I'm not going to break it down into individual elements. So I have 2 times 3, 6 hydroxides. And then over here, I have 1. So I'm going to make this a 6 hydroxides here. Okay. That gives me 6 potassiums, 6K. So how am I going to get 6 potassiums here? What do I need? A 3. So a 3 here gives me 3 sulfates. What do I have here? 3 sulfates. Okay. So this kind of reaction we're going to use in the next chapter. It's called a double displacement reaction. And it's where we take the cations and switch which anion it's attached to. So we move the iron from the sulfate to the hydroxide and the potassium from the hydroxide to the sulfate. They're just switching. Okay, so we're going to see this a lot. When that happens, all you have to do is just say, oh, that's a whole sulfate. I can count that as one thing. I don't have to split it up. Now, on some of the problems on the back, particularly the bottom one with the calcium, you don't keep the phosphate. It gets split up, okay? So because we're at the end of our time here, I'm going to go ahead and put the balance up there if you want to check yourself and make sure that you have it. And if you would like me to, on Monday, I can go through and show you how to do it. I end up with 2 aluminums, which gives us 6 chlorines, and so we need hydrogens. We have 4 phosphorus here, so we need 2 of this to balance the 4 phosphorus. We end up with 6 silicon dioxide in order to balance the oxygens over here, and then that ends up balanced. And then this one, we have 3 oxygens versus 4 oxygens. So we need a 4 in front of here and a 3 in front of there, which leaves us 1 extra potassium and 1 extra chlorine. Okay, so if that's what you ended up doing, great. I recommend write down the original and see if you can get to that on your own. But these are the harder ones, so I would have bonus points if you were to have that. Okay, you would be able to get full credit just doing the ones like we did up here. Any questions? Oh, yeah, you know what? I did that wrong. Because the calcium would have to be 3, right? Okay, so here we have 2 times 3 is 6. So this has to be 6. That's gonna give us 18 oxygens and 10 oxygens. 6 times 2 gives me 12 oxygens, and 2 times 4 times 2, 16 oxygens.